Hi everyone, welcome to the virtual lab tour of the 3-meter geodynamo experiment, which you can see behind me here and is housed at the University of Maryland College Park campus. My name is Heidi Myers and I'm a geology geophysics graduate student, and I work with the team that does the 3-meter project in Daniel Lathrop's Nonlinear Dynamics laboratory. And I'll be giving a little background information about the motivation for this project and some basic geology knowledge, why we do this, and then Sarah's going to show you around the lab. So to start out with, we should talk a little bit about Earth's magnetic field, because that is truly the inspiration and the reason why we do this project in the first place. So in order to do that, we should ask ourselves, what does the magnetosphere do for you? How do we know it's there? How does it work? And how do we study it? So to tackle this first question, what the magnetosphere does for you, what the magnetic field's presence does for you, is that it deflects solar wind. So it actually takes away the chance for these harmful high energy particles to hit us from the sun. And if the magnetosphere wasn't there, those high energy particles that come from the solar wind would actually strip away the ozone and let in really harmful UV radiation, which would be really, really devastating for life on Earth. So also the magnetosphere allows for electronics to function properly, and it allows for circumnavigation of the planet. So it was very important, especially for early explorers. And it allows for orientation and navigation of creatures with something called magnetoreception. So creatures that have this magnetoreceptive response actually use Earth's magnetic field as a way to orient themselves and to navigate across the planet. So there is some evidence that this also includes human beings. So we might need to care about the magnetic field's presence even on a personal human being level. So how do we know it's there? Well, firstly, the behavior of compasses is a really strong indication because the needles align with magnetic north, but also there's alignment of ferromagnetic minerals in rocks. So when oceanic crust is created, for example, there's a lot of material in there that actually responds to the ambient magnetic field and can lock in information about what the magnetic field behavior is at that time when it's being formed. So we see this record in the rock record of Earth's magnetic field behavior throughout geologic history as well, including times where the polarity of it, so where north and south are, actually flip. So we're able to see that in the rock record. And that's one of the reasons we know that the magnetic field for Earth has been persistent for a long time. So how does it work? So in order to talk about this, I need to introduce the concept of the geodynamo. So the geodynamo is in the name of the experiment for this lab, and it basically refers to the engine that creates Earth's magnetic field. So the basic idea with this is that Earth's core is solid, and the inner core is solid, and it's surrounded by this liquid outer core. So this inner core is made of highly metallic material. So it's predominantly iron and nickel. It's a solid metal ball, you can think of it that way, surrounded by still metallic material, but in a liquid form. And if we zoom in sort of on this outer core, inner core interface, you get this picture over to the right. So we have the solid inner core, the liquid outer core, and because Earth is spinning and there's this convection happening from this really hot material that's cooling off over time, it creates this really turbulent flow in that liquid outer core. And what's happening, because it's really high in metal content, that turbulent flow causes these electrons to spin off from the metals, which creates an electric current and thereby induces a magnetic field. So for those of you who have had a little bit of physics, that this is not a new concept, but yes, so this is how we create a magnetic field. So the TLDR here is that this spinning molten solid and liquid material at the core interacting together causes the magnetic field. So this brings up the question, well, how do we study it? We can't quite get to the core. So how do we know it's there? How do we figure out what the dynamics of it are enough to maybe forecast its behavior into the future? Well, there's two different approaches to that. So we can use models or we can use experiments to try and understand the geodynamo, to understand how its behavior not only was formed, but how it changes in time. So if we focus in on modeling, what that basically entails is building computer simulations using properties of metallic fluids. This whole field is called magnetohydrodynamics. So you see, even in the title of that, we have the magnetic part that has an influence. It's hydro, so we know we're dealing with liquids, and we want to study the dynamics of those two things interacting. And so simulations will try and replicate patterns that are seen in the rock record, so older material, as well as the human record of human beings writing down observations of the magnetic field. So of course that's going to be much, much younger. So the difficulty involved with making these models, one, they're quite complex, but two, there's a limited amount of data to use to even create the models in the first place. So that oceanic crust that I mentioned before that can lock in information about the magnetic field at the time of creation, the oldest of that crust is actually less than 200 million years old. The reason for that being that oceanic crust eventually actually subducts back into Earth's mantle. So we lose the record of what the magnetic field looked like at that period of time. So the oldest material we have is less than 200 million years old, which seems like a long time to have information, but when you consider that the Earth is on the order of 4.5 billion years old, this really actually isn't much information at all. And if we need really high quality data, which is what's needed for models, then we actually have less than 200 years. So we have this less granular, older data and only 200 years of high quality data to make the models with. So the other approach to try and understand these dynamics is actually to build experiments and see how those experiments behave and let those be an analog to Earth systems as a larger picture. So when we talk about experiments, then things like our lab come into play. So meet the 3-meter geodynamo system. So this is an artist's rendering of the system that you're going to have a tour of shortly. But I'm going to talk a little bit about what the experimental setup is, what the goals of the experiment are, and what the current status is. So looking at this setup, we have this 3-meter diameter stainless steel outer sphere. So what this is meant to replicate is that interface between the outer core, so this is like the edge of the outer core, and then the mantle would be sort of the free air outside. Then we have this 1-meter diameter inner sphere, also made of stainless steel, that's meant to replicate the inner core, so that solid core. Then in between those two large spheres, there's actually 12 tons of sodium metal that we heat up so that it's in liquid form when we're running experiments. And the reason why sodium was chosen is it's actually a pretty good conductor. And so it's a really appropriate choice to try and replicate the material that you would see at depth near Earth's core. So how this experiment runs is there's two different motor systems. One is attached to the axis of this inner sphere, so it allows for the inner sphere to spin. And then there's one attached to this outer sphere, which allows that to spin. So there's two different motor systems, which means that we can ultimately spin each one of the spheres independently of one another. And you might ask yourself why you would need to do that. Well, it turns out that Earth's core is actually moving at a different velocity than the rest of the Earth. So this is an effort to not only increase turbulence in the experiment itself, but also to replicate real-world conditions as an Earth system. So there's also these large magnets, electromagnets, surrounding, which is currently being used to help give sort of a seed magnetic field. And then the goal is to try and amplify those. But I'm getting ahead of myself. Let's talk a little bit about the goals of the experiment. What we really want to do in this lab is create our own mini geodynamo in order to understand Earth dynamics better. So by studying this system that we think is pretty close to how Earth systems are, we can then get an idea of how they behave in time, how they behave under different conditions, and ultimately the goal is to use this data to build sort of a magnetic field forecast. So this super important thing in our lives, this magnetosphere, we don't really have an understanding of why or when these polarity shifts that I mentioned earlier happen. And it would be really useful to know this information because that could drastically impact life on Earth. It could certainly impact the way our electronics function. And it would just be a really important piece of information for humans to have at their disposal to understand how our system is changing around us. So, the current status of the experiment. Well, experiments up to this point have been partially successful. So using these external electromagnets as sort of a starter kit, so a seed magnetic field, there has been some evidence that that magnetic field amplitude has grown. So that's part of the starting steps in making your own geodynamo. You want to take a seed magnetic field and make it grow. But the goal is to make it grow enough that it actually switches into dynamo action. And so we haven't achieved that quite yet. And the thinking is that while that sodium is spinning turbulently, it may not actually be spinning turbulently enough to cause the dynamo action. So it's chaotic, but we need some more chaos. So this sounds discouraging. You know, oh no, what now? What are we supposed to do with this experiment? But it's actually an incredibly exciting time for our laboratory because redesign efforts have been underway and are currently starting to happen to change the experiment structure in order to increase turbulence, so increase the chances of actually getting a dynamo. So let's talk a little bit about what that redesign plan looks like. So the idea is that we want to take this whole thing apart, change it a little bit, put it back together. That's sort of the TLDR. But the plan includes removing these motors. And you can't see it in this artist's rendering, but there's actually a suite of instruments and electronics that sit on top of this, this lid that track different changes in the experiment as we're running it. So we want to remove all of that, remove the lid, drain out these 12 tons of liquid sodium into a storage tank. And I should mention that sodium metal is actually quite volatile and it's dangerous to handle. So it can ignite, it can cause fires quite easily. And so it's a hazardous undertaking that we're doing. But we want to drain out all of that sodium, remove the inner sphere, and then the idea is that this inner sphere is actually going to get sort of a rough makeover. And when I say rough, I mean texturally rough. So our lab member, Ruben Rojas, has been working extensively on designing a setup that would allow for that inner sphere to increase extra turbulence when it's spun with respect to the surrounding liquid sodium. And so after a series of his experiments, there's one design that was settled upon, and so we're going to actually implement this on the large experiment. So there's going to be these textural changes made to this currently smooth inner sphere so that it's not so smooth anymore. And Sarah will show you a little bit more about that during the lab tour portion. But after we have made the adjustments to the inner sphere, the idea is to put the whole thing back together the way we found it so that we can start experiments again. And the ultimate goal here is to get the dynamo action. So what you'll see during the lab tour includes this massive storage tank and some of the progress in preparation in redesigning the experiment toward making our own little geodynamo in the lab. So I hope this gave a little bit of background information to you about where the experiment's coming from and what we're trying to do. And at this point, Sarah's going to take over and is going to show you the lab.
Thank you, Heidi. Here we go.
Hello, everyone. I'm Cassie Burnett, and I'm a math grad student at the University of Maryland, also an organizer of Girls Talk Math. Today I'll be giving a tour of one of the labs in this building, the Institute for Research in Electronics and Applied Physics. So come on in and we'll begin. So welcome to the lab. First thing you see when you come in is this giant cube, which houses the experiment. We also have here a tank. It's empty right now, but eventually it'll be full of sodium, as well as a shed, which houses the controls for the experiment, as well as some graduate students. So if you come this way, kind of a tight squeeze in here, but I think we can all fit because it's just me. There we are. Sorry. So now we get a closer view of the experiment. So what this is the spherical 3-meter liquid sodium differentially rotating magnetohydrodynamic experiment. So let me break that down for us. So this is a spherical experiment, as you can see. It's 3 meters in diameter. And with this experiment, you see this large stainless steel shell, but there's also a smaller stainless steel shell inside, whose ratio and radii is comparable to that of Earth's outer core boundaries. So what we like to see is turbulence. That's our flavor of nonlinear dynamics. So what we do is we differentially rotate this outer shell and the inner shell. So for example, this outer shell can move around at a rate of 4 hertz. So that's 4 revolutions per second. So what that happens with that is we get predominantly fluid wrapping around the pole. But if it's moving that fast, this door will be closed and we'll all be safe in the shed. So, the fluid, yes, the fluid is sodium, which is heated up to hot, but not too hot, just so that it's liquid, about 115 degrees Celsius. And then it becomes viscous. Right now it's at a solid state, but when we heat it up, we pump hot oil through these rivets here, heating it up to like a liquid state. And when it's liquid, it's not very viscous. It's kind of like water in viscosity. But we never mix this with water. No, 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 no. If you mix sodium and water, you get fire. So, yeah. So we have liquid sodium within. And the last thing to go over is the magnets. So we have a magnetic field that's produced by running current through these 2 electromagnets seen here. So we run current through that coils, and that produces a magnetic field that goes through the stainless steel shells and this liquid sodium within, as well as everything else. And then because of the interaction, or the fluid motion and the sodium wrapping around the pole, and because sodium is a conductive metal, that's why we chose it, the magnetic field lines become entrained in the liquid sodium, and the magnetic field also wraps around the pole. What we would like to see in the experiment is that we get magnetic field lines redirecting to go in this direction or in the same direction as the applied magnetic field. So our experiment's currently going under some upgrades in order to change the dynamics. So next thing I'll talk about is measurements. What measurements we can take. So we're gonna go to the top of the cube to check these out. So here we are. Now we have the inner and outer motor removed. Well, the outer motor was already removed, but the inner motor is removed as well. So you can kind of see we're missing pieces of the experiment to get it running. To get that whole thing to move around at 4 hertz, we need pretty large motors on top. So the measurements we can take of these experiments right now are torque, of pressure, and also the magnetic field. Particularly, we measure the magnetic field on the surface of the 3-meter experiment, and of the radial component of the magnetic field, that is the part that goes from the center and outward. We also have one probe inside the experiment that measures the cylindrical, or 2 other components as well. So we're currently undergoing upgrades. We're going to drain this experiment, so we've got most everything removed from the top, so that we can then drain the sodium from the top into that tank I pointed at below. What we'd like to do, as I mentioned before, is change some of the dynamics in the experiment. And to do that, Ruben Rojas and Artur Paravolov have been working on creating an inner sphere that has we're calling baffles, or some kind of roughness to it, so we can redirect some of this fluid motion, hopefully in this direction. The last thing I wanted to talk about here is, nope, I think that's it. So, the last thing I want to talk about is another new measurement we are taking is something called, we're interested in taking, is something called acoustic velocimetry. Because I mentioned we have torque, and pressure, and magnetic field measurements, but we don't have a good picture yet of what the fluid is doing, what the velocity field inside is doing. So what we'd like to see then is using something called acoustic velocimetry to get some sort of picture of the velocity field within the experiment, which we'll first test on the hollow tank below. So now let's go downstairs and talk about those things. Okay, so the last part of the lab tour, I want to show you the inner motor that was removed. It's all the way over here. So it's actually an inner motor as well as a frame that was used to rotate the inner sphere of the experiment. The outer motor is seen here, laying down right there. And we removed this, not by hand, but by this crane that can carry up to 5 tons of weight. So we safely removed it and set it down so that we can clear the top of the experiment. I'm going to set this right here so I can talk a little. So what we have in the upcoming upgrades are, I mentioned before that we want to have more of this motion in the fluid of the experiment rather than this motion. So what Ruben Rojas and Artur Paravolov have been doing is creating something called baffles. So adding some roughness to the inner sphere to redirect the dynamics from this direction to this direction. So here is one of the configurations that they were testing for the inner sphere in water. So this one wasn't the one that was chosen. The one that was chosen has more arrow shapes along the equator. But the purpose of these were to redirect that flow, and that was tested in a water experiment, so that's why I can't show it. The exact one here today, the exact model. Another thing that we are testing in the upcoming upgrades too is the idea of applying acoustic velocimetry to the experiment. So here, let me introduce the large sodium tank. So this tank is currently empty, and like the 3-meter vessel, it has kind of this piece right here, which will allow us to run hot oil through it so that we can heat solid sodium to liquid. But what we're testing right now on this empty tank, which is kind of easier geometrically to look at than the 3-meter experiment, is the possibility of adding acoustic velocimetry to the experiment. So what we have up here are some speakers as well as microphones, so that if you make a noise in the experiment and it's picked picked up by a speaker, then it will give us an idea of what is going on in the velocity field of the experiment, or in this case of just this tank. Right. So we have that, and we're prepping for upgrades right now. So a lot of prepping for upgrades is safety procedures. As I said, this experiment is a hazardous operation. Sodium metal cannot interact with water, or it will become flammable. It will catch on fire pretty easily. And it also can, if it catches on fire, can produce caustic smoke, which is bad to breathe. So a big part of preparing for this experiment and preparing for this upgrades is doing safety procedures and walking through the detailed plan of what we're going to do to remove the sodium from the experiment, to put it in this tank, and also to add the baffles to the inner sphere, as well as then put the sodium back into the tank and eventually spin again. So we're looking forward to that, being able to add baffles, and right now there's a bit extra PPE required because of the pandemic, so we all have face masks, but we are still making progress. So we're looking forward to adding those upgrades to the experiment, or draining the experiment, adding the upgrades, filling the experiment, and spinning again. So maybe next time you see us, we'll be spinning the experiment.